I'm Riccardo Lazzeretti. I'm presenting Bloom filter-based collective remote attestation for dynamic networks, a work made by me and Salvatore Frontera at Sapienza University of Rome. IoT devices are now commonly used in our lives and several infrastructures. Despite the benefits of facilitating cooperation and services, IoT devices present several security flaws. For example, a large number of devices have been used to develop large botnets. Of course, whether compromising devices in critical infrastructures also their functionalities could be compromised with significant impact for the society. Device attestation has demonstrated to be an efficient protocol to verify the integrity of the device. In device attestation, a verifier sends a challenge to the prover. Then the prover computes a proof of integrity where the challenge is included to avoid a reply attack and sends the response back to the verifier that can check if the device is healthy or not. Despite the simplicity of such protocol, it is difficult to make it scalable with a large number of devices. So far, all the protocols that try to make it scalable with a large number of devices that are called collective remote attestation are based on spanning trees, where the challenge is sent from the verifier to the devices close to him, and then they send it back to other devices. At this point, all the devices, after having performed the attestation, returns the results back to the verifier by following an inverse path in the spanning tree. The problem of this protocol is that if some device is moving from a position to another one, going out of the range of other devices, or if some device has intermittent connectivity, we could lose some response, so the verifier is not receiving all the responses from all the devices. For this reason, we have the need of protocol for highly dynamic networks. To the best of our knowledge, so far only two protocols have been proposed, SALD and PATS. Both of them broadcast challenges and response so that each time we can send challenges and response to any devices we have close to a node, even in dynamic networks. In SALD provides a report of each device and has a strong cryptographic assumptions. But the problem is that it has an high overhead and swarm attestation needs also minutes for few hundreds of devices. The other protocol, PARS, uses 2 bits to represent the status of a device and represent them in healthy, compromised, or unknown. The protocol iteratively converges to a snapshot of the network states. The problem of the protocol is that nodes cannot dynamically join or leave the network. And we want, in our protocol, in our proposal, to solve this problem. Why they cannot dynamically move and leave the network? Because during the setup to each device, 2 bits are assigned in a bitmap. And this bitmap is replicated in all the devices. So adding a device means that we need to add bits to the bitmap, so we have to reconfigure all the devices. We hence need a protocol that has lightweight messages for efficiency, asynchronous communication so that devices can communicate in any moment when they decide to communicate. Topology, supporting topology not completely known because the device can move. However, we need to have at least an estimation of the number of devices that are in the network. It must be flexible in joining and leaving devices. And of course, this can result in different applicative scenarios. Our protocol is based mainly in 3 components: a Bloom filter, a self-attestation, and a maximum consensus. Bloom filter is a space-efficient probabilistic data structure where we are going to, each time that we want to add an element to the set, we take the identifier of the element, we compute multiple hashes functions on his identity, and we set the position identified by the hash equal to 1. For example, we take x, we obtain that this position must be set to 1. So in this case, in this example, we have a Bloom filter where we have inserted the element x, y, and z. If we want to check if x is in the set, easily we can compute again the hash, and if we have 3 ones, we can understand that x is in the set. Another element, such as w, for example, it can happen that some position is equal to 1, but some position is equal to 0. So it's sufficient to have at least one position equal to 0 to understand that the element is not in the set. Unfortunately, it can also happen that there is some collision, and an element such u, we think that it is in the set, even if it has not been inserted. Another useful characteristic of the blue filter is that from the number of 1, we can also estimate the number of elements that have been inserted in the set. The other component of our protocol is self-attestation. Similarly to device attestation, it is really similar. The only difference is that the verifier, the element that is starting the protocol and generating the challenge, is not an external device, but it is a trusted component inside the IoT device. These trusted components need a trust light, a real-time clock that activates the self-attestation at a specific moment. All the parameters must be stored in a writable memory that is protected by the trusted component, and it has a trusted boot. At this point, the last element we need is the maximum consensus, in which, in practice, all the elements reach the consensus. In a normal common maximum consensus, each element has its value, and by talking together with the neighbors, they are going to update their value with the maximum of the values observed so far by the elements. In such a way, the maximum value is propagated through the whole network and reach all the elements. In our scenario, we are interested to a bitwise maximum, where elements can be 0, a position not set from an element, and 1, a position set by one element. In practice, we have our bitmap. Each device set, we will see in a moment, sets some bits to 1, and we want that all the elements arrive to have 1 in a position if at least one element set position equal to 1. So how we can put all the elements together? During initialization, we assign a bitmap to each device, and at the beginning we set the bitmap, the whole bitmap, to 0. At this point, when self-attestation starts, and of course all the elements are coordinated to start together, the compromised device are going to set some position according to the hashes computed on the ID to 1. At this point, we start the consensus. 2 random nodes talk together, and they update the bitmap by computing the maximum between them. In this case, in practice, the ones at the left is going to set 2 position to 1 according to the other one. We can continue the protocol, and after several rounds, of course, such information is propagated through the network, and the verifier can contact any device to obtain a network state, the network state. Of course, this network state is collecting all the information from all the devices. Even if sometimes it can happen that some devices have been out of the communication range for the whole protocol, for the whole consensus phase. Or similarly, it can happen that some device didn't receive information from all the other nodes, and in this case, we can see that there is some bits that have not been set to 1. And of course, if the verifier is going to connect this, obtains an incomplete information. And from this bitmap, the verifier can easily estimate the number of compromised devices in the network. But moreover, it can also understand if a specific device is compromised or not. A device that could be, for example, a firewall, an important router, or something like this, or something that is supposed that could be attacked. However, as we said, we cannot determine with certainty if it is compromised or it is healthy, because, as I said, it's possible that a compromised device, the information of a compromised device didn't reach in time the verifier, or it can also happen to have a false positive, so we assume that it is compromised, but it's not. This protocol is secure, as you can see in the paper, against communication adversaries that are trying to modify the messages exchanged by the devices. In this case, it's not possible simply because we rely on message authentication code, where we insert also the timestamp of attestation, timestamp of the message, and the message is generated from the trusted components, so modifying it can be easily detected. It is secure against software adversary because we are going to identify the presence of a software adversary inside the device, and mobile software adversary. This means that an adversary cannot move from a device to another one to avoid to be detected by attestation, because in the moment because it cannot know the moment when attestation starts, because it is decided by the trusted components. So what can an adversary do? An adversary that observes that attestation protocol starts and supposes that the trusted component identifies that the device is compromised, can only impede the transmission of the messages. But however, if this is what it does, we can also understand that it's not participating to the attestation protocol, but it's not going to participate also to other protocols, because a device that is not sending the attestation messages is probably compromised, and hence we are going to refuse any message from the protocol. To evaluate our protocol, we performed several simulations by using Omnet++. We set different configuration. So, for example, we modified the minimum coverage time, that is the time to obtain the information of 85 or 90 or 95% of the device. We changed the area, we changed characteristic of movements, we changed the number of compromised devices, and from that we also estimated the number of bits that should be used for in the Bloom filter. And observing the analysis, we can see that our protocol is really efficient. In fact, we can evaluate thousands of devices in a few seconds, less than 6 seconds. And if we allow higher probability of a false positive, we can also decrease the runtime to less than 3 seconds. We also compare the results with parts, and we can see that, moreover, to having permitted that nodes can easily join and leave the network, because we don't need to modify the Bloom filter, but any element can insert the elements, any device can insert its element in the same Bloom filter, even if it just joins the network. We also have an improvement of performance respect to paths. So, in conclusion, we presented the protocol for swarm attestation of networks with intermittent and moving nodes that has all paths advantages. It is also faster than paths and is flexible in joining and leaving devices. But it also provides a global view of the network that is an advantage, because sometimes a verifier is simply interested to know the state of the network, because maybe it's not able to go and interact with, to check, to modify, to correct each single device. On the other side, this protocol relies on symmetric cryptography with the same cryptographic key in all the device. That is something really common to the majority of the CRA protocols proposed so far. And it is only a probabilistic approach, so we cannot identify exactly the compromised devices, and we don't know how many nodes participated to the consensus. Thank you for your attention. If you are interested to the work, you can, I'm available for questions, and you can contact me also by email.